Hey, Tai. So Xiaoming, second lecture. Okay, thank you.
Okay, so can you all hear me okay? Okay, yeah, so the lecture today is going to be a general intro to topological mechanics. So I'll write it here. Lecture 2. So I know last week Tom already gave a lot of discussions on topological mechanics, especially Maxwell lattices. Here I would like to try to start from a slightly different perspective to talk very generally about topological states, and then we narrow down to mechanical problems. Okay, so let's start from some basic concepts. So firstly, what is topology? So many of you probably first hear the word topology when you see that picture of a morphing donut into a cup, right? I bet you all have seen that kind of picture. So basically, there are many versions of definition of what is topology, depending on what branch of topology you are thinking about. And in general, for what we are concerned, topology has to do with properties of a geometric object that are preserved under continuous deformations. So for that picture or the animation of that morphing between a donut and a cup, what is the topological property in that example? It's the number of holes or the number of handles of a closed surface, right? That is one example, but there are many other types of topological properties that you can define. So then what is topological states in general? We know that topological states nowadays is a very popular topic in the study of condensed matter physics. So in general, there are many branches of studying topological states. And what is common here is that there is a mapping between the state of the system. For example, a wave function in momentum space to some non-trivial topological space. Okay, so many of the topological states, at least for the ones we talk about here, can be thought of using this type of mapping. So how do we map a wave function to some topology, right? So if you have not studied the topological states before, it might sound confusing. How do we do this map? So the mapping is really quite geometrical. I will just start with a really basic example. So you think of a wave as a function of position, x and y, right? For example, some kind of wave propagating in space, right? And then on the other hand, you can think of a curved surface, right? So you have some kind of surface where you have x and y, and then the height of the points on this surface, you write it as h of x and y, right? And then you can make an analogy between a wave function and such a surface. And we all know that this surface could have topology, right? You can define number of holes, number of handles of this surface. And then when you map it with the wave function, more specifically, it is in momentum space, kx, ky. If the mapping from the wave function to some kind of surface in this geometric space has a non-trivial topology, we often call that a topological state. And that, as we will talk about, through the so-called bulk edge correspondence, tell you that something special is going to happen at the surface of the system. Okay? So just to give you another example of this type of mapping, if we don't think about the momentum space, right, we just think about a real space wave function, can you think of a real system where the real space wave function or the order parameter has some kind of non-trivial topology? Can you think of a real system, soft matter system, maybe? Just forget about topological states. Just think about some real space wave function or order parameter that has non-trivial topology. Yeah, topological defects, right? So real space topological defects. So you have all seen, for example, topological defects of liquid crystals, right? You can have defects where close to some point the molecules orient like this, and exactly at this point you cannot define the order parameter field. This is an example of a real space topological defect, and it is really stable. It's topologically stable. Because you cannot locally get rid of it. Right? It is protected by the topology. You can do an integral really far away from it, and you can still tell that in that circle there is such a defect. Right? So for a very, very cartoonish picture is that topological states is having this type of defects, something like that, but in momentum space. And we're going to talk in more detail about examples and how that works. Okay, any questions at this point?
So
yes?
Dislocation or discontinuation would be another example of that?
Yeah, for real space. Yeah. Any more questions? So first, I'm going to introduce a little bit of mathematical tools that will help us in establishing this analogy more rigorously. And the tools I'm going to talk about is vector bundle theory. And it is a branch of the so-called fiber bundle theory. Or let me see, it's like this. Okay, but I'm going to, so I need to put a disclaimer there. I'm not a mathematician, so what I'm going to discuss here is going to be, again, a very cartoonish picture of what is vector bundle theory, and we will just do it in a very slight, in a really like crude level, just to give you an intuitive picture. Okay, so what is a vector bundle? You can define it in terms of something like this. Here, this B is called a base space. And P is a point in the base space. So this is a point P in the base space B, okay? And the VP is a vector. Defined at point P. And we call it a fiber at P as a point in B, okay? So in some pictorial way, you can think of having some kind of manifold, some kind of surface B, right? And then on every point, you grow a fiber out of it, right? You can think of it like that, right? And then an important concept we need to use a lot here is called a section V, which is a smooth choice of V P on a region so this sigma is the region, and it's a part of the base space, okay? If you define such a smooth choice of fibers on this region sigma, then you say that I have a sector, I have a section of that vector bundle, okay? And usually we require that V of P is not 0, okay? So you can think of it as like you take fibers on this area and you give it a cut, right? So that on each point, this is a vector space. Okay, let me see if I write it. A vector space, sorry, to be more specific. So this V of P is a space of vectors, and this V, sorry for the confusion, this V is a vector in that vector space, okay? So I choose a particular value of vector in that space. So with some examples, it's going to become more clear, okay? So then if this V can be defined globally, which means all points P in B, then we call it a global section. Okay? So these are just some definitions so far, okay? Let me give you a few examples. The first example is a simple one, which is the tangent bundle of real two-dimensional space. So this is just a flat space, flat 2D plane. So this R means real. So you have two real numbers that you can use that to label the 2D flat plane, okay? And this T means tangent bundle. So here it's like I just think of this blackboard as my flat 2D plane, right? And then on every point, I ask what is the two-dimensional space that is tangent to the blackboard. In this case, it's trivial, right? The blackboard is flat. Then the tangent space is just the blackboard itself, so that I can define a two-dimensional vector space that is the same space at every point, okay? So at each point, I can define such tangent space. Each of the tangent space is spanned by two vectors, right? Because it's a two-dimensional space. I can just do it like this. Then what is a section of this tangent bundle? What did you say? Yeah, you can just choose whatever value for each point, right? A section would be, use a different color. For example, if I do something like this, I just vary it a little bit at each point. I just choose a particular vector at each point, that is a section, okay? So
They have to be continuously varying.
it has to be continuously varying. So I cannot have a defect like that. That would not, I would not call it a section because it's not smooth, okay? Any more questions? So that's a first example, and yes?
The tangent, you mean that it defines two directions, two vectors at every point?
Two unit vectors that span a 2D plane.
I thought that we started with one vector at every point.
Oh, this vector space, this VP, this space is 2D in this case. And taking the sector means I choose a particular vector at each point in that space. Sorry, when I introduced this, I confused a little bit, but this V is the vector space. Okay? Any other questions? Yes?
When you say that B can be defined globally, means that B, it's necessary to be defined in the same way in all of the four space?
Oh, it doesn't have to be the same. I can change it a little bit, but I have to continuously change it. So like maybe this one's here, this one is here. That is still valid as long as it's smooth and defined at every point, non-zero. Okay? So that's the first example. And the next example, I would like to have a bundle defined on a circle S1. So this is one sphere. One sphere is a circle. It's a sphere in 2 dimensions. Okay? So now I have a circle, and I can define different types of bundles, right? What would be the tangent bundle in this case? I just draw tangents on each point, right? Each point, I can draw a tangent line. This tangent line gave me a one-dimensional vector space, right? Because that vector can only be on this line. Okay? And, or I don't have to, it doesn't have to be a tangent bundle. It can be other types of bundles. I could do it, I say I want to use normal direction. That would also work, right? It can be negative and positive. It can be like this. So just a few more examples. I can also define a line bundle on a cylinder. So first, I draw a cylinder. And then I choose one circle on the cylinder. And I define a vector space that is along the cylinder so the points are all of the points on this line. And then I define the bundle to be those lines that are on the cylinder perpendicular to this circle. Okay? This is, again, a one-dimensional bundle. Yes?
But the cylinder is a 2D, right? The cylinder is a 2D manifold. So if you just define it on the middle line, that is just a bundle on S1. What's the difference between a bundle on S1 and a bundle on cylinder?
Yeah, that's a very good question. So here, my base space is this circle, but repeat the question. So I think if I understand you right, you're asking what's the difference between this case and this case, right?
Yes.
Or
if you have a S1, just a circle, then you grow the fiber, then you got the cylinder. If you grow a fiber like this, then you got the cylinder. But if the line bundle, if the cylinder is the base state.
Sorry. Yeah, so if like the example 2, if you have S1, that is a circle. Then if you grow each fiber like perpendicular to the cylinder to the circle, then you got the cylinder.
Yeah, so here I grow the fiber in the tangent space.
Yeah.
So I will not get a cylinder. Right?
Yes, but
That's
you
right.
can grow it in different directions.
Yeah, you can. Yeah, you can define it in that way and grow a cylinder, a line bundle on, grow a cylinder from a circle. That is also well defined.
Yeah. So
Yeah.
in this case, the base space is still S1, or the base space is a cylinder. In the example 3.
Here, the base space I think is S1.
Oh.
Yeah, yeah. So the contrasting case, this is sort of a trivial case, just pretty similar to that. The contrasting case is I can consider a line bundle on a Mobius strip, for example, which is kind of hard to draw. So I'll just try my best. It has to be something like this. Maybe I think I need to make this part a little bit nicer. So you all know what is a Mobius strip, right? You take a strip and twist and glue it together. And then now, if I just draw a circle like this. I can also define a line bundle where I just draw the line that is perpendicular to this circle, but on this strip, okay? I can also define a line bundle from this Mobius strip, okay? That's another example. And the last example is the tangent bundle of a sphere, TP of S2. So the notation here is that S1 is the surface of a sphere in 2 dimensions, okay? And S2 is the surface of a sphere in 3 dimensions. So S2 is basically just a unit sphere. You had a question?
For the Mobius strip, I'm sorry, maybe I didn't understand. Did you mean that it has to, if you're taking the perpendicular direction, then it has to go to 0 somewhere for it to be continuous?
Yeah, that's a good question. We haven't got there yet. I'm going to talk about that next.
Okay.
Yes. So in this case, I have a unit sphere, right? On each point of the unit sphere, I can find the tangent space, right? What is the tangent space of this unit sphere? How do I define that? So on each point, I can find a plane, right? And this plane is not overlapping at each point. It's not like this case. Here, you end up having the same plane. But here, it's not the same plane. And you can use the unit vectors, E theta and E phi, at each point to span its own tangent space. And that defines the tangent bundle on S2, okay? So here we talked about a few examples. Next, I'm going to ask you a question. For the 5 examples, which ones have a global section, which ones don't? Do you have a global section here? You can, right? You can take the same vector on this. Do you have a global section here? You can also do it, right? For example, you can just always go to the left. It's a global section, right? Do you have a global section here? Also you have, right? You can just do a cut, you get a global section. How about in this case? You cannot, right? You can see that if you try to follow the direction, then when you come back, it's going to point down. So at some point, it has to hit 0. There is no global section. How about this case? Do you have a global section on the tangent bundle on S2? Yes or no? So some of you said no. What was the problem? What did you say? Yeah. Yeah, it's also called the so-called hairy sphere or hairy ball. I don't remember. So basically, this is very much like you think about the hair on your head, right? So each of the hair, if you try to comb it nicely, it's going to follow the tangent direction on your head locally there, right? But if you have a perfect sphere that has hair everywhere, you can try to comb it, but there is no way that you can comb it with no singularity. Yes?
So to be defined globally means that the atlas has just a single, we use just a single mapping to go from all points to all points on V to the vector. As in, we can patch this locally with the local maps.
Right.
The existence of such an atlas doesn't mean that V is defined globally.
Right, so it has to be, I'm asking whether there's a global section. So a local section would mean that you just choose a particular vector belong to this vector space on each point smoothly on a patch. But sometimes you cannot do that globally for the whole base space. Okay? And this turns out to be one of the ways to say when you have non-trivial topology and when you have a topological state. So basically, you can relate the obstruction of defining a global section to a non-trivial topological state. So what does it mean when we say, like when we do this mapping, right? So coming back to this point, we say that we can map wave functions with geometry, right? Then we say that if this geometric object that you mapped into has a non-trivial topology, which means you cannot define a global section. What does it mean for the wave function, right? So how do we mathematically describe that? So here I'm going to sketch some basic structure of how we do that. Yes. Use the microphone, please.
Yeah. I see also a difference between the first example and the others in the sense that the first example, the space is not closed. There's no loops, right? And so is also this obstruction related to the fact that you can define loops, like the space, it comes back on itself, like NS1, S2 on the Mobius strip? So
I think it's somewhat related. So I think what you're hinting to is that if there are loops, you have to come back and it has to go back to the same value, right? Yeah. But there are loops on on R2, right? You can draw loops. It's just infinitely large. So yeah,
but
you don't
can
have
reduce them to a point, no? The loops you have on R2.
All of the loops reduce to points, yeah.
But not in the other cases, right? Or on S2 also, the loops can be reduced to a point, right?
So on S2, all loops reduce to points.
So there's no link then between the existence of irreducible loops and the obstruction of defining a global section.
I think there is some link. I'm not sure if I know exactly how to describe the link. Yeah, do you have?
If the space is not simply connected,
yeah.
Then you can define it first fundamental I1.
Yeah.
And then you'll define it with the counts because.
Itai, do you want to talk? No.
Yeah. That's right. Yeah. I think you can do mapping between loops with fundamental groups to these objects with loops. But yeah, I'm not sure what's the generic way to describe that. Okay. Yes.
Isn't defining always parallel lines in the Mobius strip a global section instead of tangent lines always parallel with the Mobius strip?
Oh, when you define it as parallel to the Mobius strip, you have such an obstruction, right? If you define it, it depends on how you confine the space. If you define it with normal direction, you still have such an obstruction. But if you make it a higher dimensional, then you lift it, right?
Even parallel is a problem because there's only a single side to the so you'll have a crossover. You'll have a crossover there also, and then the opposite is same as the parallel perpendicular. Right?
Yeah, so parallel, you mean like what I draw here, right? Parallel to the surface. If you draw it parallel to this line, then you don't have it, right? It depends on how you define your vector space. Yeah. Okay. So let's first think about like when you just think about the geometric problem like we described here, right? How do you sort of characterize what is the topology of the problem? How do you define a quantity that describes the invariant, right? So we can think of a mapping, firstly, in terms of differential geometry. So let me first write it here. So if I want to describe how this vector space varies from one point to another point, right? Because globally, that is going to be the description of the topology there. Then I need to think about quantities such as I choose any path on this base space, right? And I ask, how does this vector vary on this path, right? And this turns out to be what we call a connection. So the connection describes the variation of this vector space from points in space to the next point in space. Basically, something like this. And then we take this connection and we do another derivative. We can get the curvature. So I don't want to write it as square because it's a tensorial object, and you need to be careful with the subscripts. But basically, you first define the connection that describes how the vector space changes from one point to the next point. And then you can take another derivative and construct a curvature tensor. And then for geometric object, from this curvature, you can define the topology. So does any of you know the formula that does that? From
Gauss-Bonnet?
Yeah, the Gauss-Bonnet theorem, right? So you have 1 minus G So if you have a two-dimensional surface, you can calculate the Gaussian curvature. and you integrate the Gaussian curvature over the whole space. And if it's a closed space, you need, so what you will get, you can show that it must be an integer, and it is the 1 minus the so-called genus number, which is the number of handles. So for example, if you do this integral on a torus, you're going to get a 0, which means g equal to 1. And that is that one hole of the torus, okay? So this is the topological attribute. Okay. Then we want to establish this mapping with wave functions, right? It turns out that there is a direct link between connection and the curvature here, which we will define more rigorously as we talk through an example. So they map into the so-called Berry connection and the Berry curvature. And what they describe is basically how the phase of your wave function vary from one point to the next point. So here it is how V of P vary over space. And here it is how your wave function in momentum space vary over the change of your momentum. Okay? And then, as you can guess with the relation here, you can also do an integral, and you can show that very similar to what you have here, you also have a topological invariant, which is the so-called Chern number. So this F is the Berry curvature, okay? And you can show that this must also be an integer. It's very similar to what you have here, okay? Any questions? Yes?
Is the chain number or the on the differential geometry the G is the only one topological index? I'll say if the chain number of G is the same between of the two different structures, or then they are topologically equivalent.
They are very similar. It's more like 1 minus G.
Yeah. So if G is the same, if I have two things, and their G is the same, then could I say these two things are topologically equivalent?
Yes.
Yeah. Yes.
Yeah, that is what we mean. Yeah, so if you have two, I think the thing is if you have two very different wave functions,
yes.
Right, you put in this calculation, you get the same Chern number, then you say they are topologically equivalent. It's not the same, exactly the same state, but they have the same topology.
There's no other topological index that can tell the difference between these two.
Oh, there are many different types of topological index. Here I'm just talking about one example of them, which is one of the most commonly discussed ones.
Yeah. Thank you.
Okay. Any more questions? Yes.
Could you also have a 3D Brillouin in this?
Yes, here I'm talking about specifically a two-dimensional example. For 3D, there are other types of topological index that is not exactly mapping to this picture, but it's similar in flavor. Yeah. Okay, so we talked about this mapping between differential geometry and wave functions. And to finish this part of the generic discussion, I would like to just add one more leg to this analogy, which is with gauge fields. So the analogy with this picture here is that you can relate the connection with the A field and the curvature with the B field. And you may ask, like, why are they even related, right? So there are different ways of thinking about that. One relation is to go between gauge field and wave functions. If you think about the way you write a quantum Hamiltonian for a charged particle, right? You probably remember that you write this minimal coupling. And in this case, you can see that this A field, so let me write the whole thing. So you can make a gauge transformation. Where so when you have wave function in gauge field, you can make a gauge transformation where you change the phase of your wave function, and at the same time, you do a gauge transformation to the gauge field. And when you plug it into this minimal coupling Hamiltonian, nothing changes, right? So in this way, you can see pretty clearly that gauge field is directly related to the phase of your wave function. And then you can see that it has a direct relation with the barrier connection, okay? And another way is to think about how gauge fields relate to differential geometry. I don't want to go into too much detail here, but basically, this minimal coupling can also be related to the to how you take derivatives on a curved space, where you need to correct the fact that the tangent space vary from one point to another point, and you need to add an extra piece to make it a covariant derivative. And that is also directly related to how you introduce a gauge field to the dynamics of a particle. So then that closes the loop of gauge field, wave functions, and the differential geometry. And then the next immediate thing is to ask what is the integral or the topological quantity here. So what is that? Do you have any guess? Yeah, so if you see what we do here, right, you take the curvature, the equivalence of curvature, and integrate it over space. So what is this integral? Is this integral something that is supposed to be quantized? So if you just directly look at this, It's like calculating what's the monopole charge of the magnetic field in a closed surface, which you would say it should be 0, right? However, with a sort of a complex analogy with what we have here, if you allow magnetic monopoles in E and M, you could have such a charge. However, it has to be quantized. Again, through the minimal coupling with wave functions. Because if you have a closed loop, you can go in one path and another path. It has to agree at the other point. So as a result, the monopole has to be quantized. So then this integer that comes out here is going to be this integral divided by the magnetic monopole charge, and you get an integer, okay? So then here we see that we are sort of saying the same thing in 3 different languages. In each of the case, you have a connection that describes something, how your topological object varies from one point in space to the next point in space. And you calculate the equivalence of a curvature. And then this is the quantity where you do an integral. It has to become a quantized quantity. And it takes different meanings in each of these scenarios. Okay? So this may sound kind of abstract, right? Why are we linking these cases together? So basically, what we wrote there, the obstruction of defining a global section has something to do with that topological invariant, and also has to do with the obstruction of finding a global gauge, which we're going to hopefully link to at the end of next lecture, okay? So what we are going to do today is to first set aside these interesting mappings and connections and start from a specific mechanical example where you see these abstract concepts naturally emerge, but in something that you can actually calculate, okay? So let's consider a 1D chain. So this is a model that is often also called SSH, but it's different from the one Tom and Corentin also talked about today. And later we will see how they are actually connected. So this is a particularly simple case. I bet you have all seen this model before in solid state. So I just have a simple 1D mechanical chain, and there are 2 types of springs. I have the yellow one I call K2, and the white one I call K1, okay? How many of you have already calculated this before? Many of you, right? So in solid state, we often take such an example and use that to construct a 2-band phonon structure, right? And we most of the time in solid state cares about the eigenvalues of this problem, right? But here, all of the interesting things are in the eigenvectors, not in the eigenvalues. So to show that, let's just calculate this together, okay? So please bear with me for a moment. So I take this as my unit cell. The 2 masses are the same, right? I call this one 1 and this one 2. I can write the dynamical matrix as a function of wave number k, okay? And this has to be a 2 by 2 matrix, right? Let's construct it together. What should be the diagonal of this 2 by 2 dynamical matrix? So dynamical matrix is like you have to first write down the terms and rearrange and get it. It's a little complicated. It's easier to do it with the C matrix first, and then do the C dagger C to get a dynamical matrix. But it's not too hard, right? You can find that the diagonal terms are always K1 plus K2. Basically, for each of the atom here, you have a K2 on the left, either K2 on one side, K1 on the other side. So the total of the spring constant is always K1 plus K2. And then the off diagonal, okay? So it's basically, you can see that as the cross term between U1 and U2 is both this K1, which is within the unit cell, and the K2, which is connects to the next unit cell, right? So you have this term and this term. I suppose you all know how to derive this, right? And you can check that this is indeed a Hermitian dynamical matrix. If you take a transpose, you get the complex conjugate of itself, okay? So that's the dynamical matrix, and to get the eigenvectors, we do the usual thing of diagonalization. So in order to make it easier to write, we define K as K1 plus K2, and Z as the off-diagonal component, okay? And then the eigenvalue problem is simply D minus m omega squared I 2 by 2. You solve this problem to find the eigenvalues. The eigenvalues are m omega squares, right? And the solutions you get are m omega squares equal to okay? And then you can rewrite that a little bit into this. Okay? So then what does it look like, right? So in general, you get a band structure that look like this. So if K1 is less than K2, it's something like this. And what happens if K1 equal to K2? The gap closes, right? You get something like this. So let me just make it easier to compare. And what happens if you change the K1 to be greater than K2? The gap opens again, right? And the size of the gap on both sides is, I think, in terms of frequency, okay? Any questions? But then what are the eigenvectors? Sorry, what did you say? Square root. So, let me see. You're right, you're right. Is it like this? Let me see. Okay, yeah, that's right, that's right. Any other questions? Okay, so now let's look at the eigenvectors. I suppose omega plus minus corresponds to nu plus minus, which I write it like this. Okay? And I just need to solve this value of chi. That tells me what the eigenvector is. And I will just quickly go over it. Okay. I think I missed some sign here. This is, this is Z bar, this is Z. It doesn't matter, it's just, I just need to make the convention right, okay? And then I can just take the first line of this matrix equation. So by simply solving this equation, you will see that this chi plus minus is minus plus this mod Z over Z bar, okay? And then you can multiply by Z on both upstairs and downstairs, you get this, okay? So this is a particularly simple result, right? You see that the eigenvector is such that you have 1 and plus minus Z over Z mod, okay? So the eigenvector is just controlled by this off-diagonal value of z. Okay, there is a simple relation between the eigenvector and that off-diagonal component of the dynamical matrix. And then what do we learn, right? So firstly, let's think about how the particles on the chain move around at these two different modes, right? At different k values. Firstly, let's see what happens around k goes to 0, close to the center. So in this limit, we have nu plus minus at k goes to 0. In this case, because when this k, just to clarify, this k is the wave number, and the k1, k2 are the spring constants. The notion is a little bit confusing, but I think you can distinguish them, right? So when this k goes to 0, this term vanishes, and then it is just k1 plus k2 plus or minus itself, right? So the two eigenvectors are just this. It's a particularly simple limit, and the 1 minus 1 is the upper branch, which is the, what is the so-called optical branch, and 1 is the acoustic branch, right? So at k equal to 0, omega plus correspond to these two move in opposite ways. So to make it clear, this is the white spring, and this is the yellow spring. And for omega minus, they are moving in the same directions, right? This is these 2 points. This is this point, and this is this point, okay? And now let's see what happens at the edge of the Brillouin zone, okay? I'm going to use the space on this side. So what is the eigenvector like when you take Ka become pi, right? So at the edge of the Brillouin zone, you have Ka over 2 goes to pi over 2, and let me write the eigenvectors become, let me see. It becomes something like this. And then in order to see the direction of the motion of the two particles, you will immediately see that it depends on the sign of K1 minus K2, right? It's different from the case of close to the center of the K axis. In particular, if K1 is less than K2, you have the upper branch to be this, and the lower branch to be like this, if K1 is less than K2, right? Because if K1 is less than K2, you get a negative number here, and nu plus is negative of a negative number, so they are moving in the same direction. That's fine. Okay, so then in the other case, okay? And then compare this point and the center of the Brillouin zone. What do you see? In the case of K1 greater than K2, they agree with one another, right? For this case, the optical branch is they are moving out of phase together. And for the acoustic branch, they are moving in phase. However, for the K1 greater than K2 case, you will, by looking at the eigenvector, what you see is that this band becomes this band, and this band becomes this band as you go from this point to this point. For this case, as you go from K equal to 0 to the edge of the Brillouin zone, there is this so-called band inversion. Okay? Thank you. Yeah. Any questions? So then you may ask, like, so what, right? You just solve the eigenvectors, and this is how the particles move. What is topological about it? Why do we try to get something topological to describe it, right? So to explain that, I will use a figure that you might remember from Tom's class. Yes?
How do you get a result that depends on whether K1 is less than K2 if the whole problem is invariant under switching?
That's a very good question. What do you think is the answer?
Is it the choice of the unit cell?
Yeah. Yeah, it is how you choose the unit cell. And it is really by choosing the unit cell this way, you will say that this case is the inverted. This case is fine. But if you choose unit cell the other way, you get the opposite answer. But what is invariant is that they are different. That's the whole thing you need. Okay? Any more questions? Oh, you had a question. Mm-hmm. You mean at which point it happened? It's somewhere in the middle, depending on the relative. What? Sorry.
At which point, at the point is depends on the ratio between K1 and K2?
Yeah. Yeah, it's going to become clear. So here, as we just, where is the chalk? Just use this one. So as we just talked about, everything is controlled by this complex number, z, right? So let's think about this, how this z varies as a function of k, right? As you go around the Brillouin zone, what happens to this value of this complex number z, the off-diagonal part of this Hamiltonian, which controls the phase of the eigenvector, okay? So let's draw z on a complex plane. So this is real part of Z. This is imaginary part of Z. So what does it look like? So if I draw a circle around the first Boolean zone, which means if I let K go from 0 to 2 pi over A, what is the path of the complex valued Z? Remember, Z is defined as, let me write the, Z is K1 plus K2 it makes a circle, right? In particular, the center of the circle is at K1, okay? And the radius of the circle is K2. So in this case, if K1 is less than K2, you get a circle like this, okay? And if K1 is equal to K2, what does it look like? It touches the origin, right? This is K1 less than K2. And if K1 is greater than K2, you get a circle like this, right? And what is qualitatively different between these cases? It's, sorry, what? Yeah, whether it encloses 0. Then mathematically, if I talk about this Z as a complex number, what is the topological quantity that is of importance here? Yes? The phase winding of Z, right? So for this case, as I go around the Boolean zone, how much does the phase of Z change? Delta of phase angle of Z. It changed by 2 pi, right? And in this case, it's not well defined because at this point, you cannot define a phase angle. So this delta of argument of Z is ill-defined. And in this case, delta of argument of Z is 0. You change the phase angle, but then it goes back, okay? So now I think it's a good point for us to pause and think about how this relates to the SSH chain as a Maxwell problem, right? So what I talked about here are topological states that has to do with this gap, right? And the Hamiltonian we wrote, I just erased it, is dynamical matrix like this, okay? And you probably still remember pictures like this that Tom talked about. What is the quantity that is of interest when you do this phase winding? In that case, in the Maxwell lattice case, what is the phase that you draw this circle? I'll give you a little bit of hint, right? So in that case, if you think about the 1D rotor chain, right? So what was the quantity that is of interest when we talk about the topology of this SSH? There are two different SSH models. Here is a diatomic chain, right? These are both called SSH in the literature because both of them has an origin in the Su-Schrieffer-Heger model, right? But they are different types of mechanical analogs. Yeah, in this case, what eventually the topological state tells you is that here you have a zero mode, right? You have a topological polarization that points like this. And you have a zero mode on this side. But the quantity where you ask what is the phase winding, remember, is the C matrix, right? So in that case, you have a C of K that is, I think, C1 minus C2 e to the IKA. Okay? And you ask this C matrix because, remember, in general, determinant C equal to 0 are the zero modes, right? And I care about when the mod of this C as a complex function go to 0. And this complex plane counts the phase winding of this C matrix, which is different from this case where I ask how the phase of this Z winds. But as I will show in the last lecture, there is actually a pretty simple way to connect them, which is through the so-called chiral Hamiltonian. That Ken and Lubinsky defined, which places the C on the off-diagonal part of the Hamiltonian, where the Hamiltonian looks very much like this, but you have 0 here. You don't have the non-zero diagonal components. And as a result, you get edge modes at 0 frequency. Okay? Here, I look at the property between these two bands. And we haven't got there yet, but in the end, the edge modes we get is between these two bands. But for the Maxwell lattice problem, we're looking at actually the lowest band and the symmetric negative frequency band. And the edge mode you get is at 0 frequency, which is in the middle here. But this part of the topology is the same, and both characterized by the Su-Schrieffer-Heger model Hamiltonian. Okay? Any questions?
Is the question that were you asking about the topological environment number or something like this?
For this part,
Oh, the one with the circles? With the circles?
yeah, here it is draw the complex number of determinant of the compatibility matrix as K goes through the first Boolean zone. You see how the phase of this C changes. Yeah. And here we look at how the phase of the Z changes, but they are almost the same. Look, Z has this form, and C has this form. It's a very similar problem, in fact. Okay?
What is the meaning
topological polarization. That's a very long story. So I'm going to, if that is of interest, I can add a part in the last lecture to go back to that, because here we are mainly talking about finite frequency topological states. I don't want to detour too much to this, but I can add that to my last lecture to define more explicitly what is the topological invariant from the compatibility matrix, and how do you go from that to get the topological polarization.
That system have a topological polarization like this one, or not?
So they are different. So the topology is the same topology, but how it maps to the mechanical modes is different in these two models. Okay? Any more? Yes?
If I choose a special SI3 chain which ends with a spring instead of a rotor, could I still use this way to tell where is the rotor?
What kind of SSH? This one?
If it ends with a spring, the dash line instead of the rotor.
Yeah, these are the springs, right?
Yeah, if I remove the rightist rotor,
Yeah.
yeah, if I remove this guy, don't remove the spring. Keep the last spring.
Keep the spring.
Then could I still use this way to tell where is the zero mode?
I'm not sure what do you mean by this dangling spring.
Yeah, if I just leave a spring there, then it's also very floppy mode, right?
Oh, you mean like I have a mass point here, but it's not a rotor?
Yes, it's not a rotor.
Yeah, then you have a trivial zero mode and a topological zero mode.
Oh, okay.
Right? Because you removed a constraint.
Yeah.
You have two zero modes.
But in this way, if I calculate everything like the topological invariant, then I can only tell where is the topological zero mode.
That's right. Yeah, because when you calculate the topological index, it's a bulk property. It doesn't ask any question about the edge.
Yeah.
Right? It tells you when you cut the edge, where do you gain extra zero modes?
Thank you.
Okay?
So is there a finite frequency topologically protected mode that lives in the gap of that
Yes,
system?
yeah. I haven't got there yet,
Oh,
but
okay.
that's the next thing.
Okay.
Do we still have time, or should we continue tomorrow? 8 minutes. Okay, let me see. So I think I can actually just define the actual index, and then we can finish it here. Right? So how do we? So we see that it has to do with the phase winding of Z, right? But mathematically, how do we write that into a nice integer using the wave functions? Right? That is the so-called Zach phase. Okay? And this is the so-called Berry connection. So as we talked a little bit in the very beginning, the Berry connection, similar to the connection in the geometry case, it describes how the vector space moves from one point to its neighboring point. Here, as you can see, it describes how the wave function varies from one point in momentum space to the next point in momentum space. And you calculate this connection and do the integral over the first Boolean zone. What you get is this so-called Zach phase. And in this case, you will get two values, pi and 0. Pi is the K1 less than K2 case. and 0 is the K1 greater than K2 case. So it has a direct connection with the change of the phase of Z around the first Boolean zone. And that is actually a nice practice question. You can prove that this formula, when you take this phi to be this wave, this solution, this two-dimensional vector, and do this calculation, you will find this. And then the winding number for this problem is Zach phase divided by pi. So we say here you have winding number 1, here you have winding number 0. And those are the two distinct topological phases of this 1D chain. And then what is the consequence, right? It has to give you something on the boundary. And in this particular case, the way you look for the edge modes is actually the interface between these two different phases. So basically, if you draw a chain like this, so as you can see, this part is a nice 1D chain like we defined. This part is also a nice 1D chain. But we alternate a little bit in the middle because after white, it should be yellow, right? But I did white 2 times and then white, yellow, white, yellow. This is an interface. And I can also do an opposite interface of 2 yellow here. And you can finish the whole chain. And you will see that there are exponentially localized modes at these interfaces, and the modes are in this gap. So it is also a nice practice question for you to just numerically do a chain like this in real space. For example, you do a chain of length 20. 10 follows this type of unit cell. 10 follow the other type of unit cell. You construct a dynamical matrix in real space, and you calculate the modes. You will see them. It's a pretty easy code to write, and you can actually see the edge modes. Okay? And proving why this index gives you that edge modes is not trivial. It takes many steps. And in general, the picture you can think about is usually like here you have a gap, right? This is at plus minus pi over a. Here you also have a gap. But these two gapped states are of different topology. So at the interface, you necessarily need to close the gap. You can only change from one gapped state to another gapped state of a different topology by closing the gap. As a result, there are these edge modes in the gap when you put them together. Okay? And there are a number of subtleties with this particular version of SSH model, which makes it less robust than the rotor model, which I'm going to touch upon a little bit next class. So I think this is a good spot to finish today. Thank you.
Okay, are there questions? Okay, if not, let's head home, and we'll see you tomorrow at 9:30.
Okay, thank you.